Okay, so here we're going to look at chapter 18, starting off with symmetry here. And to be more precise, symmetry of shapes in a plane. Later on, we'll look at symmetry in a polyhedra. So plane, two kind of dimensional figures here. Okay, so we're looking at symmetry of shapes on a plane. So cutouts, things that, think of it on your actual tabletop, so two-dimensional here. And when we talk about our symmetry here, we could talk about reflection or a line of symmetry is what they're referred to. And what we're kind of looking is that it's in a mirror image. So here we see this snowman where if we make a vertical line down, if we were to put a mirror there, the left side and the right side will look exactly the same. So think of it as mirror images here. So left side looking the same as the right. Some nice examples with manipulatives to play around with this is just folding a sheet in half, having them cut out some shapes, and then opening it up, and we'll see that there will be a line of symmetry with the left and right side looking exactly the same. So maybe some type of a Christmas tree figure or so. We also could talk about rotational symmetry, so rotating in objects. And so here what we do is we kind of fix, whoops, let me get back there. So we fix an actual point, think of it as putting a thumbtack, and then we're going to spin the object around there. So here we have a square, we have kind of a thumbtack right in the center, and then we're going to go ahead and spin it. And if we could spin it so where when we rotate it, we get the same shape again in the same orientation. So rotational symmetry here. And we could see for a square, we could actually, if we do 90 degrees, we'll get the same shape again, 90 again. So the rotational symmetries are 90 degrees for a square here. Now to keep track, we want to, when we rotate an object or change it, we're going to use this prime notation. So if I were to rotate this square, then counterclockwise, so the new position of where one of these points was at, so here is my point, I'm going to rotate it counterclockwise here. And what will happen is that A will now move to a new position. So that new position we would call A prime. Okay. And so the question we want to ask is, right, this does not line up to the original figure, right? Does it line up to the original figure? And in this case, it doesn't. Just doing a very small rotation from here is not going to be enough, right? We could go a little bit further, as they saw in the next figure. So now we're actually moving it even further down to this point. So moving A from its original position to A prime, and that still doesn't line up. But if we move it enough, we could see that A will actually line up with A prime here. So doing that 90 degrees. There we go. And so that's always a question. Does it line up, right? And that's what we say a rotational symmetry. And in this case, it'll have a rotational symmetry of 90 degrees because every 90 degrees, it'll go ahead and line up. If we were to move this yet again over here, then again, we would line up with the exact figure. Okay. So at 90, 180, 270, and 360 degrees, this would occur. Okay, so a symmetry of a shape is any movement or geometric transformation that fits the shape onto the same set of points it started with. So again, that the orientation is going to end up looking, it's going to match up that figure again. So here we talked about this reflection on this kind of Christmas tree figure. When we do that, it will match up again here. And oops, yeah, let's actually go here so we could see this. So some activities here is, what are the reflections of symmetry? So if we have this triangle here, what are these reflections? So if I were to draw a line vertically down, I could see that the left side here would match exactly to the right side here, right? And what will happen is we're really just rotating it. So think about this as an axis. And so the triangle is kind of moving towards you where it's going to move around. So to kind of illustrate this, let me put some notation here. If I were to kind of do an axis here and flip this around in 3-dimension, kind of move up towards you, then your L would be over here, so that'll be L prime. Your M would be over here, and then your K will still be at the same point, but we'll still call it K prime. So moving this kind of towards you, so fixing it on that axis and it coming up towards you around, so flipping it on its back side. And so here we could see that again, so our reflection here. This example one down here, this figure does not have any reflections or rotational symmetries. And just by looking at it, you could see that it does not have its symmetries there. Typically, some good examples to introduce this, not just with geometry figures, but introducing, mixing up with other lesson plans, alphabets, right? Does this have some type of symmetry? Do some of these letters here have symmetry? Right, so taking a look at some of the letters, not just shapes, or other ways we could start kind of looking at that as well. Okay. And going back to this triangle here, we could actually see that. Where did we go here? Here we go. So our letters, going back to this triangle, that was not the only reflection of symmetry. Notice I have several here. And another one. So going through the altitudes, right, or bisectors of these angles here. And we could see that again with even these letters, right? Reflective horizontal with the letter H there. Or even vertical, the letter H there. So fun activity to look at other shapes, even letters, to see if we could identify those. So rotational symmetries here. Again, fixing a point and rotating this object. Let me get rid of these here. So this would be K prime, then M prime, and then L prime. And those angles of rotations we could see would be 60 degrees, 120 degrees, and 180 degrees. And again, start thinking about this. How many sides does the shape have? And then how are we coming up with these angles, right? So 360 degrees divided by 3 gives us 120. So actually, did a little goof up here. Those are not correct there. So it would be 120, 240, and then 360. There we go. That looks more like it. So rotating all the way around, right? So rotational symmetries, when we talk about those, we like to put the degrees that we have on that. Think about some of the letters as well, right? Do some of these have any rotational symmetries as well, right? And we could see the letter I, right? If we flip it all the way around, it's definitely going to have one at 360. And then even the halfway point, we could flip it upside on its head, so at 180 degrees as well. And so, like we said, this example, this actual shape here does not have one, and you could visually just see it. It doesn't have that symmetry that sticks out. Okay, what about an isosceles triangle here? So an isosceles triangle, and again, going vertically down here, right, the original and then our reflective rotation here. Now remember, what we're trying to do here is when we draw this axis here, right, think about it as it's getting flipped towards you. So we're getting that piece of paper and turning it on its back, okay? And so we see when that happens, then that C will go to C prime, and B will actually come back here to that B prime position. So flipping it around. So the original and then our reflective rotation, and we remain, the shape looks exactly the same, right, in the same position there. And so here's some nice discussion. So why equilateral triangles have to be equal angular. So when we talk about the definition of an isosceles triangle, we don't necessarily include that they have the same, you don't have to include same angles and same length. One is sufficient because we know if we have the same length, then those same angles will also be the same. So likewise here with the equilateral triangle, right, if we know those sides are the same, then we know those angles are also going to be the same there. So this is a good activity to play around with. But again, going back with our hierarchy of shapes where we don't have to define a shape with every characteristic, right? As long as we have some rules in play, we could just go ahead and say an equilateral triangle just has the same sides at the same length. And then we could imply that the angles will be the same as well. So as we explore characteristics of shapes, these rotations, reflections, symmetries will be helpful as well. Other characteristics they could start looking at. Let's look at this example. Does a parallelogram have any symmetries? So let's think about that. And so here we have a symmetry of shapes, right? So parallelogram, does it have any of these symmetries here? So let's look at the rotational first. Here's rotation, putting a thumbtack and kind of spinning this around. And so we'll see that if you do a 90, it's not exactly going to line up, right? But if we move this around from A to AC, so this actually has to go all the way around here. So 180 degrees, we will end up with the same, with that symmetry there. And then think about these line symmetries, right? We'll doing these diagonals here, right? Could we see that these are going to be exactly the same, right? Opposites. There we go. Obviously, going vertical, horizontal will not yield those. And just a fun activity, letting students explore, playing around with these different shapes and to see what these symmetries consist of. Okay. And this is actually focused on mathematical practice number 7 here. looking at these reflection symmetries, rotational symmetries, right? Looking at objects with certain degrees. 180 is a pretty common one here. And then how could the structure of symmetry help you think about the truth of other conjectures you made about properties of special quadrilaterals? So again, we've talked about making definitions kind of their own. And the more we explore these shapes, the more characteristics we see, the more meaning we're going to be able to put to these as we try to come up with definitions and explain these different shapes. So here's another activity here, or exercise 3. And let's look at this figure. Let's look at the regular pentagon here. And we'll first see how many reflective symmetries it has here. Okay. And so we're seeing that there is one going down, vertical there. And we see that the left side and right side will be exactly the same there, like if we had put a mirror in between. And there's actually going to be a few more here. What if we went from the other vertices? There we go. And yet another. There's a third, a fourth, and then a fifth. So think about how many of these reflective symmetries we have and how many sides this regular pentagon has, right? If there's relationships between those. So 5 sides, right? 5 vertices, and then 5 of those reflective symmetries. And does that hold for a regular, right? For a regular polygon, right? Would that happen if this was not a regular pentagon, if we had one side that was different? Okay, so again, seeing that one side is the same as the other, right, in any orientation. Let's look at rotational symmetries. Okay. And again, if we were to move our P counterclockwise over to P prime, or to the T position, we'll call that P prime, and then T would move over to the S position, T prime, etc., all the way around. So putting a thumbtack at point M there, we'll get the same orientation again, right? So the shape will have that symmetry. And there's actually more than one here. We could continue moving P to that second position, to S there, right? Or even down to R, right? To any of these vertices. If we move it around, we're going to end up with that symmetry. So 5 of these rotational symmetries. And again, 360 divided by 5, because that's all the way around. They're going to occur at every 72 degrees in this case. Okay, and I'll leave the regular hexagon for you to explore a bit. So the takeaway here, the symmetry of shapes, is that not only do symmetric shapes have a visual appeal, but they make the design and construction of many manufacturers' objects easier. Okay, so we want them to play around, visualize this, get very familiar with them. And then symmetry is often not found, so it's okay to get shapes that do not have those symmetries. As we're looking to observe symmetry in shapes, we also want to make sure we observe that there is also an absence of symmetry in other shapes there.